In this webinar, we are going to discuss about nanomaterials, the technology to develop nanomaterials offering multiple properties carries tremendous potential for the development of applications in all industry and research sectors. That's the main reason why I thought I will compose this presentation, and we will discuss about multi-wall carbon nanotubes, boron nitride nanotubes, graphene, metal and alloys nanoparticles, and some composites with nanomaterials. In general, I would like to discuss about Goodfellow and introduce you a little bit Goodfellow company. So we are a 70 years company. We are providing, as Prasad said, metal alloys, ceramics and glasses, polymers, compounds or composites throughout all the industry sectors and research as well. We have over 70,000 products and we have customers over 60,000 worldwide. We do also bespoke processing services and we don't have any minimum order quantity. So we are also ISO certified, and our technical team, together with the scientists and engineers which are combining Goodfellow, are here to help you and assist you further with your research and any other project that you are having. So we're going to discuss today about multi-wall carbon nanotubes and especially the carpets. Usually we're discussing about carbon nanotubes in a powder form, but in this one we're going to discuss about carpets. But let's say a little bit about carbon nanotubes. So carbon nanotubes are cylindrical molecules that consist of rolled up sheets of single layer carbon atoms. They are also consisting of several concentrically interlinked nanotubes. Their length can reach for several micrometers, even to millimeters. As we can see here, the length of our carbon nanotubes can go up to 1,500 microns. And they can be also, they are in a form of a sheet, which is, you can see the macro picture there also, and then also some SEM or TEM pictures of a cross-section of these. These multi-wall carbon nanotubes are chemically bonded with sp2 bonds, and these bonds is an extremely strong bond that forms of the molecule interaction. This feature, combined with boron, with carbon tubes' natural inclination to roll up together via van der Waals forces, provide the opportunity to develop ultra-high strength, low-weight materials with high electrical and thermal properties. So for this particular material, we can see the properties and estimate the graphitization level by the Raman spectra. The ID to IG band is 0.31, which means we have a great graphitization level. The usual production of carbon nanotubes, multi-wall carbon nanotubes, the usual production methods for multi-wall carbon nanotubes are usually the arc discharge method, laser ablation of graphite, and CVD process. These particular carbon nanotubes are produced by a floating catalyst, CVD method, with an horizontal quartz reaction tube under certain gases. The parameters were carefully selected to provide maximum yield of carbon nanotubes growth, high packing density, as well as high graphitization level, as we have already discussed, and we can also estimate from the Raman spectra. Also from the SEM and TEM images, we can identify the average diameter, the length of the length of the carbon nanotubes, and by TGA analysis, we have derived the purity and the oxidation temperature, which is very remarkable. What is very important about these carbon nanotubes, which are carpets, which are refined as carpets or forests, is that they are freestanding. Usually, the growth of carbon nanotubes and the forest, especially, or the carpets, is used. The growth is occurring upon a catalyst, or like a copper or nickel or iron plate. But also it can be, you can use and grow the carbon nanotubes on a quartz substrate. However, these ones are freestanding, which gives the optimal electrical properties of these carbon nanotubes. We're going to discuss about in the next slide about the applications of multi-wall carbon nanotubes. I know that this is very general, but how we're using these carbon nanotubes? Usually they're composites, all right, and usually we're calling carbon nanotubes nanocomposites. These are highly attractive alternatives to conventional composite materials due to their mechanical, thermal, and chemical and electrical properties. Carbon nanotubes are characterized by excellent conductivity, tensile strength, or even flame retardance. So these composites are promising to offer increased wear resistance, strength, and adiabatic properties, as well as weight reduction. The hollowing, for example, they have a hollow interior. The hollow interior can be filled with various nanomaterials, or separating and shielding from surrounding the environment. This, let's say, feature or property is extremely useful for drug delivery applications, which are not included here, but I have the medicine there sign. Also, the carbon nanotubes are used in sporting goods like bicycle frames or tennis rackets or golf clubs. The antistatic property of carbon nanotubes are used in textiles called smart textiles. Also, because they are lightweight and they have high strength, they're used in automotive composites or aerospace. For example, it is estimated that 30% of the weight of the aircraft can be reduced. The electrical properties are very important for the carbon nanotubes, I would say more than anything else, and the strength as well. Their electrical properties are extremely sensitive due to the effects that they can understand very well the charge transfer. So sensors can detect, for example, gases, molecular recognition of different, let's say, proteins. For example, as well, they're used for flexible hydrogen sensors. And this is a research that it has been used with single-wall carbon nanotubes and palladium. Also, the electron transfer capabilities of these carbon nanotubes are giving them their ability to use in electrodes. So, alternative to graphite electrodes, for example, because graphite is usually used in electrodes in lithium batteries. Also, electrical properties such as conductivity and the sharpness of their tip. It is very well known that smaller tips radius of curvature, then the more concentrated electric field we will have, the higher field emission also we will have. So these materials are used for field emitters displays. Another example of carbon nanotubes is that they are generating fine peaks in optical absorption and emission. So, and that's the importance now for the forest that I have already discussed. So, aligned multi-wall carbon nanotubes emit polarized light by electrical current heating. So, the higher the brightness emission we will have at a lower voltage compared, for example, to tungsten filaments that they already been used. So we can understand that the application of multi-wall, the properties of multi-wall carbon nanotubes give a great range of application. So it is discussed and it has been claimed that boron nitride nanotubes will be the next generation material for the fourth industrial revolution. Why I'm comparing them? Because boron nitride nanotubes and carbon nanotubes, they're more or less the same structurally. So they have both low density, they have both high strength and stiffness, and they have both high thermal conductivity. However, the boron nitride nanotubes, though they are structurally the same with carbon nanotubes, they alter in their structure boron and nitride atoms. Thus, they have also higher temperature, they can withstand in higher temperature, and also they are electrical insulators, because they have a band gap of 5.5 electron volts, while carbon nanotubes can be metallic or semiconducting, having a band gap of around 2 electron volts. Oops, sorry. What we have done here is that we have produced boron nitride nanotubes. However, the usual production method is ICP method, which is called the inductively coupled plasma method. And usually they are synthesizing yarns, which looks like, or I would say fiber-like materials, which they look like cotton balls, all right? And this is very, very, I would say, although they have all these exceptional properties, it is very, very difficult to disperse them in different matrices, all right? However, here I'm introducing you a powder-like form, which is very, very important for dispersion. This powder form of boron nitride nanotube has been produced by ball milling, actually crystalline ball milling of a boron source, which is using stainless steel. And keep in mind, stainless steel and stainless steel vessels and balls. All right. So you have a source of iron and a source of boron crystalline powder. From the XRD, we can see the amorphous boron in the beginning. So we can see the by ball milling all these by ball milling the boron nitride nanotubes, we are resulting to an amorphous boron. All right. So in the beginning, the amorphous boron, we can see the black line on the XRD pattern, and we can see some peaks, which means that either that the amorphous boron is not being completely or perfectly amorphous, or we can have some iron contact. While milling further the boron nitride nanotubes, we can see the blue line, which is we don't have any peaks, so we have a perfect amorphous boron powder. And after that, we have a special heat treatment, which is let's say reforming the amorphous boron to boron nitride nanotubes. This special heat treatment, we might have some iron content, all right, in this special heat treatment. However, we are purifying and we can remove the iron content or the iron from the stainless steel vessels and the balls if we will put them in let's say ethanol solution, and we can remove them with just a magnet. It's very easy to remove the iron content. So we have calculated experimentally the thermal conductivity, and it has been shown that it's 600 watts per meter Kelvin, which is very, very important. Also by SEM analysis and TEM analysis, we have defined the layer distance and the wall thickness of these boron nitride nanotubes. Further purification can be also occurred, and the part is the most important is that these boron nitride nanotubes, they can have a purity of 90%, which is, I will say, it is the only one material with such a purity commercially available worldwide, and that's why it's very important. Somebody will ask about what will be, let's say, the applications of boron nitride nanotubes. Where can we use them? So boron nitride nanotubes, as the carbon nanotubes, can be used as fillers in different matrices, all right? So we have electrical insulating and thermal conducting materials for IT devices. For example, our great research group has conducted this project, and we can see that the boron nitride nanotubes composites with 50% weight percentage of hexagonal boron nitride nanoparticles, while with 0.5 weight percentage of boronite nanotubes, they can conduct heat better than just the hexagonal boron nitride nanoparticles or just the boron nitride nanotubes. What is happening when you're having the boron nitride nanoparticles and the boron nitride nanotubes is that the nanotubes are working as heat conduction channels. By this, we can see that we have embedded them in different matrices like the polybutyrene, polystyrene, or PMMA, and the thermal. We have enhanced the thermal conductivity. I will say that it's as much as 3 times higher than the pure polymer. Also, what I would like to say here is that the coefficient of thermal expansion of the hybrids have been reduced because of the interactions between the polymer chains and the boron nitride nanotubes. This has been measured with the microthermal mechanical analysis, and this is very important for IT and devices because they reduce the thermal stresses in a printed circuit board, for example, which is laminated. Also, I would like to say that this thermal stresses is very important because it can reach reach to failure as well of this PCB that we have in IT devices, our IT devices. So the boron nitride nanotubes will offer great opportunity and great a great result in this occasion. Another potential, I would say, application is for catalytic their catalytic effects for removal of environmental hazardous elements, and maybe why not enhancing the cracking of petroleum engineering. So this material, as we can see, it has converted the carbon monoxide rate higher than 95% at 200 Celsius degrees, where the carbon monoxide is usually converted. You can also use or dope palladium with palladium nanoparticles and as low as 1 weight percentage. So in that case, the catalyst that you are having is not only the palladium, but or palladium is not so expensive as it would be. So I think that is a very important application as well. In general, I would say that boron nitride nanotubes are not used in day-to-day examples. So I couldn't find any example of them to present you. So I would say that the boron nitride nanotubes, they are suitable materials for containers of radioactive waste because they have this great neutron absorption and shielding by boron. Their enhanced chemical inertia as well of boron nitride nanotubes favors the biocompatibility, so we can use it as nano carriers for drug delivery systems. Also because the boron nitride, as we all know, is a ceramic material, so they can use as fire retardant cables, and we have already discussed about it while it was embedded in the PMMA or the polybutyrene or the polystyrene in our previous example. And we have already seen that it has enhanced their thermal conductivity. It can be used also in aerospace and nuclear engineering, or in general in polymer and ceramic composites. If I may be excused, I would like to say that this is, I will use a metaphor. This is the valley of death, which is often used to describe the gap between academia innovations and their commercial applications. And honestly, I couldn't find any real commercial application for these boron nitride nanotubes in that case. I'm sure that they are going to be used in future, and we're going to see them more, and we're going to find more applications about it in real life. Let's discuss a little bit about sustainability. Somebody may ask why I added this slide, all right? However, I would like to say that green materials and sustainability is a key challenge in industry, not only in industry, but also in research. Green materials is a term that is used to engulf materials that adhere to the environmental principles throughout their circle of life. And in that case, by that we will have a minimal environment impact. Materials manufactured from natural resources, for example, like materials that we extract from nature, and manufacture other materials with environmental friendly processes or environmental friendly chemicals or non-hazardous chemicals. And also how we're using them or distribute them, or are we going to reuse them, or are we going to recycle them or compost them is very important for the future. So reducing the amount of solid waste entering in landfills and carbon footprints is a positive and benefits commercially and environmental our world. So Goodfellow will say has introduced a list of green materials in our portfolio, and green or materials that have been produced by a green process and green methods, or non-hazardous or by non-hazardous solvents. And one of them, and it is very, very interesting, is our green graphene. I would say that probably most of us, we all know about graphene, and it is very, very and widely well known. So I will just say how this green graphene is produced, and I'm not gonna discuss about green graphene in general, because it's more or less what I've said about carbon nanotubes. So green graphene is produced by means of a highly scalable chemical-free process that involves the breaking of methane. We all know that methane is a very potent greenhouse gas that is a harmful byproduct of ambiguous processes like farming, landfill, or palm oil milling, and actually we can use this hazardous gas, and we can we are processing actually in and decomposing into hydrogen and elemental carbon in a plasma reactor. Actually, this reactor is vibrating, and it's very interesting. So another interesting factor is that the elapsed time from methane gas entering the plasma reactor to the point when graphene is formed is less than 1 second. That means that the production of graphene can be massively. I mean, it's amazing. At that point, few layers graphene are formed, and we can have the 2 to 10 layers graphene, as you can see on the table. And also afterwards, we have a special heat treatment which is producing, and I'm sorry, but it's proprietary information, I cannot reveal more. And it is producing the predominantly 1-layer graphene with exceptional properties. This process, as I said before, doesn't involve anything else. No additives, no catalysts or metal impurities, just the methane in a hydrogen atmosphere. The resulting graphene nanoplatelets, as we can see by the SEM pictures and images, is slightly scrambled. Also, it is very, very thin, and that we have we have identified the thickness of the graphene layers. So one of the most important, let's say, features of this graphene is because, as I said, it's slightly crumbled. They do not stack together, all right? But while if we are going to produce graphene by exfoliation process, for sure they are stacked. So this feature is ensuring optimal electrical, thermal, and mechanical performance. We have identified and estimated the electrical conductivity, which is very important for graphene, and we have already, I suppose that we already know that graphene is a highly electrical conductive material, and the thinnest material in the world, and the lightest material in the world, and the best material in mechanical strength as well. So we have, as I said, estimated the conductivity by a 4-point probe measurements of compressed pellets, and also the surface area of graphene, which is very important as well, by the BET method. Having no catalyst, this graphene shows that it can be used as a filler in applications I would say that the applications which are very sensitive to metals, such as biomedical applications, sensors, fuel cells, etc. However, on this slide, and I would say it intrigued, and also it made me being more interested about graphene and their biomedical applications and its biomedical applications. While I was attending an MRS presentation, and I saw these two examples. So I thought I should share them with you. So a few layer graphene can be used for fillings in teeth. Fillings are typically made of mixtures of metals such as copper, silver, tin, or they are composed of powders, glass and ceramic powders actually. So it's the white filling that we have. Also we can use fluorinated graphene into fillings. This improves not only the mechanical properties and the corrosion resistance, but also the antibacterial properties of the graphene. For example, the antibacterial of the filling, sorry, not the graphene. For example, the antibacterial properties of the filling has been proven and has been increased about 85% with only 4 weight percentage of graphene as a content into the fillings. In addition, I saw this one that graphene can be used for teeth whitening, which was very interesting. And the reactions that you can have with cobalt tetra, I hope I will say it correctly because it's a little bit tricky, this one. The cobalt tetraphenyloporphyrin with hydrogen peroxide is enhanced because of the high surface area of graphene. And we can whitening our teeth in less than 70 hours, as we can see. All right, that is very interesting because this graphene, the previous graphene, it was just a research project. Have we seen graphene in day-to-day life? Apparently we have, and we are using it. Maybe we do not know it. So, for example, Ford Mustang and the other model, Ford Mustang and another model of Ford, which is called F-150, has used graphene foams, graphene composite foams in several components, such as pump covers, engine covers. And it has been proven that the mechanical properties have been improved by 20%. Also, the heat and endurance has been improved by 30%, and also the noise reduction has been improved as well from the foams. If you compare the foams from graphene with the conventional foams that they were already using it. So this is great, and it is used to day-to-day life, in day-to-day life. Another example of graphene is a company UK-based, which they have made trainers from graphene composites, and it's called Innovate. So these trainers have outlasted about 1,000 miles more than a typical or conventional trainer, and it has been scientifically proven to be 50% to have 50% wear resistance than a conventional trainer. Cost-effective solution, right? So these are the day-to-day examples. In general, graphene can be used might be used to aerospace to enhance the mechanical performance of the parts that they're used in satellites, for example, or because you can produce lightweight materials. It can be used in transport, for example, on the planes, where you can coat graphene coatings has been developed for de-icing. Also in construction, for example, I have seen several research papers about self-healing cement. In desalination, where you can have a mechanically robust graphene membrane, and by the nanoside pores and the reactivity that graphene features towards the polar and non-polar water pollens, you can, let's say, maximize the permeability, the water permeability, while it can separate particles that are based on size, shape, and also charge. And you can clean the water, for example, and you can have a healthy life, let's say, or for example. Also, graphene has been used in sensors or conductive inks. These conductive inks can be water-based or solvent-based, and nowadays they're playing a very important, let's say, part in our day-to-day basis. And also graphene has been used in medicine for drug delivery, and it can be functionalized with proteins, for example, or other organic groups. Also, it has been used in textiles and smart textiles. And at that point, I will say stay tuned, because Goodfellow is going to bring a very good material about which is going to be used in textiles, and it has extremely amazing mechanical properties and adiabalistic properties. I'm going to say that also it can be used in sport and leisure as well, and it is already being used in carbon nanotubes in tennis rackets, for example, or bicycles. In general, graphene can be used, I would say, or is being used in different applications and in all sectors. Another very interesting, let's say, series of products that we have introduced in our green production is the metal and alloys nanoparticles that are being synthesized by green chemistry, so no hazard solvents. Again, I cannot reveal a lot of information about the production method because it's proprietary, but I can say that we can have high purity metal nanoparticles and alloy nanoparticles or metal oxide nanoparticles from sizes 1 nanometer up to 100 nanometer and different shapes. That's very important. So we can have shapes like needles or spherical shapes or square shapes or even irregular shapes. In general, we know that nanoparticles cannot be used as alone, all right? So usually we are using biopolymers, or we are encapsulating them with silica, or we are decorating them on carbon nanotubes or graphene, we are fractionalize them with different groups. And this is the way we are embedding them in different matrices. The matrices can be a polymer, can be clays, can be even metals, molten metals, of course. I'm not going to say a lot of information about it, but we can discuss it further and you can ask me further questions about it. However, we know that the nanoparticles, we have an ideal, let's say, opinion about it, but are they completely spherical? Usually they are not. All right, the size and the shape are not uniform. Even if we have them as a core cell, the core cell is not uniform, the surface fractionalization is not uniform, or we might have surface contamination depending on how we are synthesizing them. Also, it is very important to understand that they are changing with time, all right? So the size can change, the functionality can change, and also the aggregation can change. So sometimes that's the reason why we can see that the conductive inks of graphene, let's say, or of silver paints are precipitating, and we have to disperse them again. Also, because of the high surface area to volume ratio, we can see some oxidation or changing the chemical stage or even the shape of the nanoparticles. This is very important because we have to understand why we are bending them and which matrix we are going to use and why. I mean, are we going to use a polymer that they are going to, let's say, affect this phenomena, and they're going to keep them on the same shape, or the chemicals, or keep the chemical state or not. So we have to be very careful on when we are selecting our matrix. The application of nanoparticles. I'm sorry about this slide, that it is too condensed, but the application of metal nanoparticles, or in general alloy nanoparticles, are huge and extremely. So I did it on purpose. So I will just discuss about some examples of nanoparticles. So for example, we can have platinum nanoparticles for hydrogen fuel cells. So hydrogen fuel cells are a clean energy alternative that they use hydrogen and oxygen to generate electricity. And currently, we're using platinum metals, bulk metals, for the electrodes of the fuel cells as a catalyst. If you will use platinum nanoparticles, then for sure you can improve the efficiency, because you will have an increase in the material catalytic activity, and also in the reduction, you're going to reduce the metal usage. So you're not going to use a bulk platinum nanoparticle, platinum electrode. If you're going to use nanoparticles, then the quantity that you need is less, for sure. So it's a cost-effective solution. So since the current that is generating on the electrodes is proportional to the active surface of the catalyst, the nanoparticles will improve the power density due to their high surface, as we said, area to volume ratio, compared to the bulk materials. For example, you can use also on electrodes a combination of carbon nanotubes decorated with platinum nanoparticles. This can reduce the platinum content as well, so a more cost-effective solution, another one, and produce the same surface area of the active catalyst. And for example, this is a very nice example, I would say. Also, gold nanoparticles, we know that they have been used and they have great biocompatibility, and they are featuring excellent optical, electrical, physicochemical, and surface plasmon resonance characteristics. So these are used for these reasons are used in biomedical applications, and this feature can alter by changing the shape, the size, or if you're gonna fractionalize the gold nanoparticles with different groups, or usually organic groups. As a result, they have been used in various biomedical applications, such as sensors, drug targets for drug delivery, in imaging applications, or photothermal and photodynamic therapy as well. Lately, I came over a request in the technical the technical help desk, and it was about copper oxide nanoparticles. That's the reason I decided to tell you about it. So copper oxide nanoparticles for bioapplications such as biodetectors or other bioapplications are recently being used. And the particle size is less than 100 nanometers for sure. And they display enhanced microbial activity towards pathogenic microorganisms. So I thought that this is very important. And while we're talking about pathogenic and microorganisms and viruses, the next slide is about COVID and how nanotechnology can help with battling COVID-19. Nanotechnology nowadays is not only has a great impact in our society and also in COVID-19. For example, silver nanoparticles have been used in sanitizers, or graphene-based masks have been produced, and actually it's a UK-based again, which is called company which is called Planartech, and they have announced the mass production of graphene-enhanced antibacterial face masks. So that's the reason why I try to connect the biomedical applications and this slide as well. And I hope you enjoyed it. So stay safe, stay at home, and we will save lives. Next slide is about 3D printing and some as well, and some examples. So 3D printing provides many advantages. So such as simplicity and reliability and precision. And it is the most widely method used in additive manufacturing process in the whole, not only in the industry, but also in research as well. That's the reason why I picked these two examples. And of course, we know that in general, PLA and ABS is used widely in 3D printing. So if we will enhance the PLA with graphene or nanodiamonds, then for sure we're going to have better and improved performance. So the PLA with graphene, it is enhanced. Sorry, the graphene in PLA is enhancing the properties such as strength, thermal conductivity, anti-static, and it has also dimensional stability. So also it provides better impact performance. While having nanodiamonds, which at this case they are spherical nanodiamonds, and we're enhancing the PLA filaments, we have also higher thermal conductivity, and what is the most important is that the nanodiamonds are less abrasive against irregular shape fillers that they are used in commercially. So this leads to lower the nozzle wear, so we have less wear resistance in the nozzle, and also offer enhanced printing speeds. So because as we all know, diamond, and especially nanodiamond, it has lubrication properties. 3D printing in general is used in different applications. So it has been used from, let's say, in motor vehicles, so for accurate and aesthetic models or rapid prototyping, and it has been used, for example, in motor parts. So we have stronger and lighter vehicles. 3D printer in 3D printing in general is used to produce complex parts. So yes, we have been seeing consumer products and, for example, toys, and for example, Lego. It is produced by ABS. And in consumer goods like bicycle parts or even other things like tools. And of course, it has been used in medical applications for customized prosthetics and implants. And what is very, very important here and nowadays is that by using also artificial intelligence programs, you can predict the mechanical properties. So you can predict the failure, you can predict the stresses, and you can improve your component. So you can have an optimal mechanical strength of your component, or a very strong component that it won't fail so easily, while you have if you will compare it with a conventional one, which is produced by, let's say, cutting with diamond tools or whatever we are going to produce it, whichever method you are going to produce it. And going to conclusions at the end. I hope you enjoyed, of course, the video, and we have to say some of our conclusions at the end of the day. So sustainability has been expanded even from nanoparticles. As we said, it's 2D materials, green graphene, and it's very important nowadays for the nanotechnology. We discussed about the valley of death for the boron nitride nanotubes, for example, and there's going to be a collaborative model between the academic world and the marketplace. For example, graphene has been used, and this is a collaboration between these worlds, from Ford or from this trainers company. And I would say that at this point, if you would like to follow us or join our social network, you can see it there. And please stay tuned, as my colleague, Mr. Adam says, will talk about materials in aerospace and automotive next week. Thank you very much for your attention and for your time. Any questions, please? Prasad?
Yes, thank you, Aphrodite, for your wonderful presentation. We have a time constraint, and there are so many of those questions, and I see a lot of comments about the nice presentation. So we will start taking questions. And yeah, I'll just read out the questions for you. What Raman spectroscopy data determines about carbon nanotubes?
I'm sorry. Can you repeat, please? I'm sorry. Which spectroscopy?
What Raman spectroscopy data determines about carbon nanotube?
What the Raman spectroscopy can derive about the graphitization level. So let's say the ID to IG band, or ID is the diamond band, let's say, so it's the sp3 bond, while the IG is the sp2, while the IG is the sp2, the graphite bond. All right, so if this ratio is, let's say, close to 1, then we can understand that we only have diamond-like, so it's imperfection. So the less it is, the closer it is to 0, then it shows that the better the graphitization level, and the less impurities we have as well. So more or less is what you are deriving from a Raman spectroscopy, if I understood well the question.
Thank you. The next question is how to study the mechanical properties of CNT, that's carbon nanotubes.
That's a very nice one. That's a very nice one. It's difficult to the mechanical properties. Yes, that's very difficult. So what I have done in, let's say, at the university is having the same, more or less the same material. First of all, you can calculate them theoretically, all right? So despite the theoretical calculations, if you have, let's say, a polymer, and then you're for sure you are let's say you're calculating or estimating the mechanical properties with mechanical, of course, characterization and analysis. And then if you're enhancing the with carbon nanotubes, then also you can measure the mechanical properties. Unfortunately, theoretically, the mechanical properties have been calculated. So you cannot actually, because it's in a powder form, and even if it's not, it's very brittle. So only micromechanical properties, or sometimes you can have micromechanical properties and you can calculate the mechanical properties by using, like, let's say, SEM combined with micromechanical properties. It's a very complicated, this one, unfortunately. So you are just estimating it, or theoretically calculating it.
I will go to the next question. Before going to the next question, I see a lot of attendees are dropping out. So I just wanted to inform you that we are arranging the second webinar on in the area of aerospace and automotive by Goodfellow. So you will soon be receiving a link. Do not forget to register for that webinar. We are hosting that webinar on 15th of May, that is next week. So please do register once you receive the link for the webinar. I will move on to the next question. How can we use carbon nanotubes in energy sector?
That's a very nice one. All right. So I think I've mentioned some of the examples for the energy sector. Let's say fuel cells. All right. So in fuel cells you are using or lithium batteries. All right. You are using graphite as an electrode for the catalyst. All right. So let's say that this electrode can be enhanced with carbon nanotubes. The carbon nanotubes has such a surface area that will improve the catalytic absorption and the catalysis in general, the process. So either by time or let's say the reactivity will enhance the reactivity of the catalytic process. So that's how it's going to be used, for example, in energy applications. And I think I have mentioned some examples of those.
Okay, thank you. The next question is there any limitation with carbon nanotube due to that boron nitride nanotubes will be used in next generations?
That's a good one. No, I don't think, because both of them, they're used for different applications. So the carbon nanotubes can be used for semiconducting application, while the boron nitride nanotubes can be used for insulating applications. They are not semiconductors, or they do not conduct electricity. All right. So there's not going to be a limitation. No, I cannot see that why it can be a problem.
Thank you. The next question is interesting one. How nanomaterials will help to treat corona, which has troubled the whole world? Can you throw some light on this as well?
That's a very interesting. Actually, I have attended another webinar about nanomaterials and virus from MRS, and it was very interesting. So what I have heard is that they are using gold nanoparticles, and they are modifying them by functionalize them. So this functionalization, then they carry the drug, or let's say the vaccine molecules. So by the photochemical properties of the platinum nanoparticles, they can target where the virus is, and they can release the drug. So more or less is what they were talking about. Or you can use silver nanoparticles because of the antibacterial properties, and they said that they are going to coat the mask, so that you are not gonna let's say have the coronavirus, so you're not gonna inhale it. Also nanoparticles, because they're very, very small, and the virus, we know that it's very, very small, it's around nanometers. So let's say that you have a conventional mask, the mask will, the fibers inside won't be in nanometers, while if you're enhancing this, let's say, fabric with nanoparticles, so there is a bigger possibility to prevent the permeability of the virus and nanoparticles. So this is more or less how they said they're going to help and assist with coronavirus, the nanoparticles. I hope I answered that.
Thank you, Aphrodite. We are short of time now. We will have to stop here. I know there are many more questions which are there in the list. Don't worry, we will get back to you with the answers to those questions. We will send across those questions to the Goodfellow team and get back to you. Thank you so much to all those who joined, and thank you everyone, those who asked questions as well. And as I said, we will get back to you with the answers. Thanks again to Dr. Aphrodite for taking time out from your schedule for our Indian researchers today. Thanks to my colleague Adam and Hossein and from my colleague from Merck India team, and also Goodfellow team, Simon and Adams, for helping us hosting this webinar. Our next webinar, as I said, is on aerospace and automotive. You will soon receive a registration link to it. Do not forget to register and join the webinar. Thanks again. Hope to see you all soon. Stay home, stay safe, and those who are working in lab, please take care. Thank you so much. Simon, any closing comments from your side, please?
No, thank you very much, Aphrodite, and thank everyone who attended. It's a very exciting and important area of study. I think if anyone does have any questions that they feel are unanswered, please, we will get back to you. But you can contact Aphrodite and her team directly on technical@goodfellow.com. So we do answer every single technical question that comes to us. Again, thank you very much for the Merck India team for setting this up. Thank you again for Aphrodite for your excellent presentation, and thank you all mostly for attending. Appreciate this time, and it's been great to have you. Thank you very much. Thanks, Prasad.
Thank you.
Thank you, Prasad. Thank you all.
Thank you.